Yeah, so I think we'll start, Yeah, so welcome back everyone for the second talk of Enumeration lecture series. So now we have Professor Kevin Buzzard. Professor Kevin is a professor at Imperial College London. He earlier used to work on algebraic number theory and has contributed to several programs such as Langlands program and so on. Now he has switched fields and is now working on proof verification. He is well known for his contributions to Xena and Lean, which in fact he organizes them so that undergraduates can get a better handle to verify their proofs. So over to you, Professor Kevin, who will now talk about how powerful theorem provers can be and how they'll affect the future of mathematics. Yeah.
Thank you very much. I should say in particular, thank you to the organizers for letting me do this talk on Zoom. I find it much easier to use than many of the other options. So as has been said already, I'm not a computer scientist, I'm a mathematician, but now I seem to work in an area which is somehow somewhere between mathematics and computer science. And I'm going to talk about whether computers can prove theorems. So let's see if it works. It works, great. So I want to start by talking about computing versus reasoning, just to make sure that we're all very clear about what the difference is. So the traditional use of computers in mathematics is to compute, right? That's somehow what computers used to be humans, right? In the word computer used to be a job. A human would have to do many additions and calculations as computing became more important in life. And then these computers were mechanized and we had mechanical computers, which were different to the human computers originally. But this is what a computer traditionally does and what mathematicians use computers for. They compute. But now, of course, we've moved along a long way from these primitive computing machines that we used to have. We had the abacus and then the electronic adding machine, the mechanical adding machine, and then electronic calculators. And now we have computer algebra packages, things like MATLAB, Maple, and R, and Mathematica, and many, many other packages. They compute for us. And these systems are commonplace in mathematics departments and in other science departments, universities around the world. Maybe you've used some of these systems. Maybe you've been taught how to use these systems. And these are not obscure things. And this is not to talk about these systems at all. I want to talk about reasoning with computers, which is something else. So this is a talk about using computers in mathematics to reason, which means to prove theorems. So reasoning programs, here's the name of some reasoning programs, computer proof systems: Lean, Isabelle Hol, Isabelle ZFC, Coq, Hol4, Hol-Lite, MetaMath, Mizar, and Agda. These are all computer programs like MATLAB and Maple and Mathematica. But probably you haven't heard of these systems, at least if you're in the mathematics department. If you're in the computer science department, maybe you have used them, but mathematicians have probably not heard of or used any of these systems. And because well, I don't really know why. But let me show you what the difference is between these two systems. So let me start by switching to. Let's fire up a nice cheap and cheerful. This is Parry GP, a nice cheap and cheerful computer algebra system. And so let's list all the primes less than 1,000, right? So for I equals 1 to 1,000, if is I can't remember how to use it. If is prime I, print I. Does that work? There we go. And you see instantly the computer has just printed out the primes less than 1,000. I mean, he just hit enter, and there we got them. And I guess we could even look for all the twin primes less than 1,000. If is prime I and is prime I plus 2, then we could print I comma I plus 2. Oops, maybe we should put a space between them as well. There we go. So there's a list of all the twin primes less than 1,000, or and we could just we could go up to 10,000 instead, and there you go. It's just these things just appearing instantly. I guess we could go back to primes. If is prime I, print I. There. Are there infinitely many primes? Right. We could. Those are all the primes less than 10,000. But let's go up to millions and billions, and now you can see the computer's just evaluating more and more primes for us, and so it looks like there's probably infinitely many primes, right? But can we actually prove there's infinitely many primes? Not with a computer algebra system, right? That's exactly what they can't do. So how do we prove there's infinitely many primes? Well, of course, we do it. We do what Euclid did, right? We do it on pen and paper. But you see, what you can do in Lean. So Lean is, a computer program. So here it is, and it's some kind of, it feels a bit like a computer algebra package. Let me import the tactics. Let me import. Where are the primes? Datanat prime. Let's there. So I'm gonna prove a theorem using a computer right now. I'm going to prove there's infinitely many primes if I can. And the first thing I'm going to do is I'm going to start by importing, Lean's theory of primes. So let's go. Let's examine how are we going to prove there's infinitely many primes. So first of all, we have to figure out how to state it. So let's say for all natural numbers n, there exists a prime p. There exists a p such that n is less than or equal to p, and and nat dot prime p. There. That's the statement. That's the statement that there's infinitely many primes in Lean. That's what it looks like. You see, so it feels like it's a computer algebra system, but we're not getting it to do calculations. We're claiming there's infinitely many primes. We're saying this is a theorem. So I guess nat dot prime kind of looks. Maybe I should do, if I do open nat, we should try and make this look nicer. Then probably I can do there prime p. So how are we going to prove this? So begin, sorry, end. There you go. So here's the idea. We're going to prove a theorem. I'm going to type in this proof on the left-hand side, and on the right-hand side of this screen here, you can see Lean's brain. You can see what Lean's currently thinking. So currently, right now, it says we're going to prove this theorem. So how are we going to do it? We're going to start, I guess, we're going to go intro n. Let's let n. So we're going to let n be an arbitrary. Let n be an arbitrary natural number. There, intro n. And now you see things have changed a little bit on the right. You see, before and after something. You see, this is some interactive system. So right now, this says n is a natural number, and we've got to prove that there exists a prime p. We've got to prove there exists a natural number p, such that n is less than or equal to p, and p is prime. Well, how are we going to do it? What's the? I guess we need to stop and we need to think about what the maths proof is. What's the maths proof that there's a prime larger than n? I guess we could let p be the smallest prime factor of n factorial plus 1, right? So that's what we want to do next. Let p be the smallest prime factor of n factorial plus 1. So how are we going to find the smallest prime factor of n factorial plus 1? I guess we need to, what I want to do is I want to show you how a beginner user might try and use this, someone that really doesn't know their way around the library at all. We want to find something about the smallest prime factor. So let's search for smallest prime factor. Here we go. What's this? The min fac orcs. This looks good. Min fac orcs. Aha. Min fac the square of the small. Here we are. This is what we want. Returns the smallest prime factor of n. So what's this? There we go. This is called min fac. There seems to be something called min fac. Let's have a look. What's this min fac? Check min fac. If I hover over this, min fac, it returns the smallest prime factor of n. So okay, that's great. So let's let p be min fac of n factorial plus 1. Oh, now we have an error, and the error is that Lean doesn't know this factorial notation. So we should enable natural number notation. Yeah, so open locale nat. That should fix this. And now there we go. Great, this has worked now. So P is now defined to be the smallest prime factor of n factorial plus 1. And now the idea is we're going to use P. There. And now we've got to prove two things. We've got to prove firstly that n is less or equal to P. And secondly, we've got to prove that P is prime. Okay. So how do we go about doing this? So, okay, let's have HP. I claim that P is prime. So why is this? So you see, now we've got two problems. I'm claiming that P is prime. So now we've got the thing that we used to be proving. We used to be having to prove that M was at least P and that P was prime. And now we've got another goal here. Now we've got to prove that P is prime. Obviously, that's going to be helpful for proving this one. So how are we going to prove that P is prime? Well, didn't this min fac, this min fac is supposed to return the smallest prime factor of a number. So it's going to be somewhere in the library, the fact that this thing is prime. So we're going to let's look through the library search. Let's look through Lean's library, and we have an error. It's gone red, right? It says library search failed. So this is very strange, because if P is the minimal prime factor of something, then surely it should be obvious that this is prime. You know, that this should be in our library somewhere. So what's going on? Why can't I prove this automatically? And the reason is, if you look in the small print, where's the small print again? It's just occurred to me. If I hover over this, can you see the pop-up? Can you see that pop-up that says returns the smallest prime factor of n not equal to 1? I can see something on my screen. It just occurs to me that you might not be able to see it.
We can see it as well.
Okay, so it says returns the smallest prime factor of n not equal to 1. So there's an issue here that maybe n factorial plus 1 is equal to 1. So let's have hn. I claim that n factorial plus 1 is not equal to 1. Not equal to 1, right? And this is just, let's skip the proof of this. And now all of a sudden, this works, right? Now it says, great, we can do this. So now we have a proof that P is prime, but we had to assume that n factorial plus 1 was not equal to 1. Okay, because if you think about it, if n factorial plus 1 is equal to 1, then we can't take the smallest prime factor. You see, it's being very pedantic. It says, wait a minute, you've taken the smallest prime factor of this number. What if this number's 1? 1 doesn't have any prime factors. So what do you mean? So now we've got to prove that n factorial plus 1 is 1. Why is n factorial plus 1 not equal to 1? Well, n factorial plus 1, it's not equal to 1 because n factorial is positive, right? Let's just call it h2. N factorial is positive, right? N factorial is bigger than 0. 0 is less than n factorial, right? And that should be in the library. So let's just have a look by library search. Let's find this. There we go. So 0 is bigger than n factorial. And so now maybe we can do some linear arithmetic. Is this going to work? No, it still won't work. Okay. So I claim that have h3. I claim that n factorial plus 1 is bigger than 1. Right? 1 is less than n factorial plus 1. And this must now be obvious. Linear arithmetic. There, that's great. And so now we know that, so now let's look in the library. No, library search. No, okay, rotten luck. So I'm going to have to think, why is this not true? 1 is less than n factorial. How are we going to prove that n factorial plus 1 is not equal to 1, given that n factorial plus 1 is bigger than 1? Is that really? Oh, so I'm stuck. Well, okay, I'm going to have to guess. You see, this is what I didn't want to do. I'm going to have to guess what this is called. This is going to be called NE of LT, right? That's a good name for a function. NE of LT. Let's do this. What does NE? There we go. NE of LT says that if x is less than y, then x is not equal to y. So it's going to be H3, and that's a proof that 1 is not equal to n factorial plus 1. So now let's symmetrize it. Why? Oh, I can get rid of this. There we go. So you see, you can make progress, but it's somehow a struggle. So now we've got to prove. Now this is ridiculous, right? Now we've got the p is prime, and now we've got to prove that n is less than or equal to p and p is prime. So I guess we could do refine. I don't know the proof of the first thing, but I do know the proof of the second thing. There we go. And so now we've only got to prove that n is less than or equal to p. And you see the proof goes on like this. We can slowly build the proof. How do we prove that n is less than or equal to p? I guess we prove it by contradiction, right? By contra H4. So now we're assuming that n isn't less than or equal to p, and we've got to get a contradiction. So what this is silly, right? It says not n is less than or equal to p. Why don't we get that into a more push neg? Let's push neg at H4. So there we go. Now it says that p is less than n. You see, and now we can prove that p divides n factorial, and we know that p divides n factorial plus 1, and we deduce that p divides 1, and we finally deduce that p is less than or equal to 1, and that contradicts the fact that p is prime. So
Hello.
you see this. Hello.
Yeah, I'm Dinaka CS here. I have a question from two incidents that took up on 1977 and 1980. You may know Shakuntala Devi, a great human computer. She have been computed the 23rd digit 201. 23rd root of a 201 digit number.
Aha.
And the multiplication of two 13 digits number.
Aha.
Okay. In those periods, how scientists and mathematicians have been program the codes, and how they execute these answers to verify those answers that was given by a human brain.
I'll take this question at the end, if that's all right. There's plenty of time for questions at the end.
Okay, sure. Thank you.
So, but ask me again at the end. I'll give you an answer. So you can see that somehow we're very, very slowly walking through this proof that there's infinitely many primes. And you can clearly do it, but you need to learn, you need to learn how the system works. And it's, it's slow going. But you see, of course, we can just cheat, right? We can just get rid of everything, and we can see if it's in the library anyway, right? There we go, and it's in the library. So there we go. It's in the library already. It's called exists infinite primes. And this is somehow the crucial thing. So there you go. There's a complete proof for you. But you see, we've cheated, and we can right-click on this, and we can go and look at the proof in the library. There's the proof there. You see, it's ended up being 1, 2, 3, 4, 5, 6, 7, 8 lines long for a pretty straightforward thing. So this is what reasoning is, right? This is not doing calculations. This is proving theorems. So now let me go back to here. So the transition from school to university, this is something I have to deal with a lot in my job as a university teacher, because at school, the kind of things that we emphasize, is mostly computing, right? It starts off very early. First of all, we ask things, what's 2 add 3? You work it out on your fingers. Then we start asking things like, what's 7 times 8? And we don't say work that out on your fingers. We say look it up on a table. And then we start saying things like, what's 783 add 373? But again, you don't do this on your fingers. You perform an algorithm, right? You know what 3 add 3 is. You know what 8 add 7 is, and you carry 1. And then later on, we start asking people to do things like invert this matrix. Here's a 3 by 3 matrix. Convert, compute its inverse, compute its eigenvalues, this sort of thing. These are computations. You might feel like you're proving something, but actually you're doing computations. You differentiate cos of x squared. Right? How do we differentiate cos of x squared? I guess we use the chain rule, right? The chain rule would help with that. But you see, what is the chain rule? Theorems like the chain rule, they're not at school. You're not told the proof. You see a picture, you see some lines, you say, derivative is like this slope here. It's not a rigorous proof. It's a proof by picture. So theorems are presented as tools. The students learn the tools, and then they become better at computing. You see, the emphasis is on learning to use the tools. This is the important thing. So it's true that there are some proofs in school mathematics. For example, angle chasing theorems, Euclidean geometry. Euclid was about proofs. Euclid had constructions and proofs in his elements, but the angle chasing theorems, things like proving that triangles are congruent, or proving that angle at center is twice angle at circumference. These are very basic proofs, again with a lot of pictures involved, that we teach young school children. And later on, you might learn induction and learn about proof by induction. But these are the limits of the kind of things that we see for proofs in school. It's mostly calculations. And then we go into university mathematics, and what happens straight away is that there's more emphasis on proof. Right? Instantly, like you're beginning. You do a beginning course in proof in a university mathematics degree, and you'll learn things like proof that a composite of injective functions is injective, or proof that equivalence classes give you a partition of a set. Equivalence class, you have an equivalence relation on a set. And I have students saying to me, well, what's the method? I don't know the method. And this is an interesting question, because maybe there is no method now. Maybe you have to start thinking. The idea about computations is they teach you the algorithm, they teach you the method when you do the computation. But now all of a sudden, we're out in the open here. We've got to come up with proofs by ourselves. And many university students find it very difficult. And of course, by the time you begin your introductory analysis course, you see the chain rule again, and you thought you knew it was true. You've been using it for many years probably. But actually, these weird pure analysis people, they want to give you a proof, and the proof is some very technical epsilon delta argument. It's quite an elaborate thing, and maybe you're even forced to learn this proof and regurgitate it in an exam. The kind of the most ridiculous exam question that asks you to when in your life will you not have access to a formal proof that the chain rule works, right? There are these weird points. One, when you don't have access to the internet. Like, when does that happen now? More and more, you find you have access to the internet at all times. I go to work on the London Underground, on the subway, and between tube stations, I don't have access to the internet. And London Underground are going to fix that in a couple of years. There's going to be access to the internet even when you're traveling between tube stations. Right now, they just have all the platforms are activated with Wi-Fi. But more and more, the internet is everywhere. So when can you not look up the proof of the chain rule on the internet? Like when you're in an exam, this is becoming more and more ridiculous. But these proofs are out there, formal proofs, careful proofs that the chain rule works. And so, now you have to start wondering, is that the kind of question that we should be asking people on exams? And more generally, how should we be teaching? How should we be teaching students? And how should we be teaching them proofs? And the really weird thing is, we do introduce computers very early on at university. We show undergraduate mathematicians how to use computer algebra systems to compute. So we say, great, you know how to invert a matrix, but now you don't even need to know, because you can use, if you want to invert some 2 by 2 matrix, you just type it into a computer algebra system, and the system will invert it for you. But where do we teach the computer proof systems? This thing that I was just using very, very slowly and laboriously earlier. Where do we teach those things? We teach it to the computer science students. That's what's happening at universities around the world. Computer science students are learning how to use these computer proof systems, and mathematics students who are suddenly beginning to have to really wrestle with the idea of proof, they're not being taught these things at all. So isn't that a bit strange that we have these tools that can do proofs, and you just see them? They're kind of primitive, right? They're very, very slow. They do work, but they're rather primitive. So here's the natural question. Why are we teaching computer scientists about computer proof systems and not mathematicians? And this brings us to the more general question, why do these computer proof systems even exist, right? Why are people writing computer proof systems if we can use them slowly to prove mathematical theorems, and we're not even teaching them to mathematicians anyway? The moment we start teaching them, things are going to get better. Things are going to get easier. We're going to have sort of more graphical interfaces. We're going to have pop-ups which suggest theorem names. Things are going to get much better. But the important thing is we need to get mathematicians to actually learn how to use them. So let me talk about why computer proof systems actually exist. They exist because of the Curry-Howard correspondence. Right? The Curry-Howard correspondence, loosely speaking, I mean, it is a precise statement, and there's even more precise ones involving category theory. But let me stick with Curry-Howard. It says that there's some kind of correlation. It says that a mathematical proof and a computer program are in some sense the same thing. Right. Sure, more precisely, checking to see that a proof is correct and checking that a computer program has no bugs. These are very, very similar processes in the sense that you can get one system which is capable of doing both things. And so it turns out that these computer proof systems are used in they're used in industry, and they're used in computer science departments to find bugs in code and to prove that certain code is bug-free. And this is one of the main motivations for designing these systems. Bug finding. So is bug finding actually important? So it turns out that bug finding is really, really super important, because if your computer doesn't work, it's really annoying, right? And in fact, there are examples now where bugs have cost people a huge amount of money. If a bug is making a hospital work, then you don't, if a computer program is making a hospital work, you don't want a bug in that program. You don't want the lights going out, or the machine stopping working, or all the patient information database to suddenly start crashing. And you can't find, you need to find a patient and you don't even know what bed they're in. The Pentium FDiv bug, this was a bug in a chip that meant that on extremely rare occasions, this chip would divide a real number by another real number incorrectly. And this bug needed to be fixed. Intel was just like, well, it doesn't happen very often. But then there was an outcry in the industry. And Intel ended up having to replace every single one of these buggy chips, and it cost them $500 million. So somebody I know that I've worked with on Lean's Maths Library, he developed a lot of the topology in Lean's Maths Library, and he now he was a computer scientist, and now he left academia and got a job in industry, and he now works for Apple, and he is verifying that the iPhone operating system has got no bugs in, because for Apple, this is super, super important, right? You just want your phone to work and just behave seamlessly, and you want to make sure that nobody can hack it, right? Those are really important things as far as Apple is concerned. And so this guy is now being paid, a lot of money to verify that, to use these kinds of tools to check that these operating systems have got no bugs. So here's the current state of things. These computer scientists have made these powerful systems, and these systems can do mathematical proofs, because proofs are the same as bug checking. Proof checking is the same as bug checking, but mathematicians don't use them. That's the current state of things, and that's what I want to check. So what systems are available? I mean, right now, there are 3 main systems for doing mathematics, because just because these systems can do mathematics, it doesn't mean that people use them to do mathematics. So Lean it's free and open source. Anyone can download it. There's instructions on the Lean community website. It's written by written by a guy at Microsoft Research. So this is, it's got big money behind it. Microsoft are backing this one. And this is the one I chose. And then there's two other very big players in this area. They're much older, Koch and Isabel Holl. These are also both free and open source systems. And all three of these systems have got mathematics libraries. All three of them have got proofs that there's infinitely many primes. So you don't have to struggle through proving that thing by yourself. And I personally have chosen to work with Lean, and I know much less about the other two systems. And more mathematicians are working with Lean than the other two systems, more classical mathematicians. But if you want to experiment with other systems, I think it would be good if there was kind of competition and rival systems developing bigger and bigger mathematics libraries. I think that would be interesting. So I had to choose one of the systems because, I got interested in whether I could help my students to learn things like the formal proof of the chain rule using these systems. Maybe I could write very, very clear proofs with step-by-step instructions and hide the difficult stuff behind some imports, and just see if I could train my students to use one of these systems. So I chose Lean. So I now teach I teach mathematicians how to use computer proof systems. I teach undergraduates, and if you want, you can look at my course for this year. I'll put this in the chat. Where's my Zoom? Will I find the chat? Oh, there's the chat. Here's the chat. I'll look at the chat at the end as well. So you can use this, self-study and learn Lean. Learn Lean if you're a mathematician. But more and more resources are appearing for mathematicians if you want to learn Lean. So there's something in the chat. And it's suitable for self-study. And I'll mention something else later. One of my PhD students is actually running something specifically for Indian undergraduates. Actually, I have an Indian PhD student. I'll talk about her later. So I think they might be useful for undergraduates. And can they help mathematical researchers? Well, you've seen that using Lean can sometimes be very slow. But let me show you two papers from the Annals of Mathematics. This is the top pure mathematics journal. Here are these two papers. These links are live. I can click on this link. Let's open this. Let's open this link in a new tab. Let's see what have I got here. Here we are. This is the first link I showed you. So this is a technical paper in the top maths journal from 2004, right? And it proves that a certain moduli space of polarized varieties is quasi-projective, right? This is what's proved in this paper. It doesn't matter if you don't know what any of these things mean. A moduli space of polarized varieties is quasi-projective. And so let's look at this second link here. And this theorem here is another theorem, and also proved in the Annals of Mathematics. Oh no, it's not. It's the same theorem. So let's try the other. Here we are. Here's the other one. This is two years later, 2006, the same journal, the most prestigious pure mathematics journal. And this proves that certain moduli spaces of polarized varieties are not quasi-projective. He gives explicit examples, Janos Kolar. And he remarks in the abstract, this contradicts a recent paper. See, it just says here, this contradicts a recent paper. So we have two papers in the most prestigious maths journal. And if you use the main result of both the papers, then you can prove that 0 equals 1. Okay, so then you can prove the Riemann hypothesis. Right? You can prove anything you like. And no retraction has ever appeared. There's no note on either of these. There's no note on either of these. There's nothing saying, by the way, the main theorem in this paper is wrong, right? But the main theorem in one of these papers must be wrong, because if you take these two papers and put them together, you get a contradiction. So one of these papers is wrong, but there's no indication. If you're in with the in crowd, if you've got friends who are algebraic geometry researchers, they'll tell you which one is wrong. But if you don't have friends in high places, then you're gonna struggle to figure out what's going on there. So is there a problem with the mathematics literature? Another question is there a problem with my slides? And there's some little dots here that shouldn't be there. So I need to learn more about this Reveal MD platform. So is there a problem with the mathematics literature? Well, yes, but no, right? Because the experts know what's correct, you see. And the experts can smell a bad proof. They know one of those papers is wrong, but the paper that's wrong has got a bunch of brilliant ideas in. You know, parts of it are right. And anyway, there's always been errors in the mathematical literature. And the thing is, it works, right? It works quite well, the system we have currently. Why should we change it? You know, should we, you know, this is a very naive idea. Maybe we can try and fix mathematics by making all the maths researchers use all these computer proof systems. But you've just seen how they work, right? Some people call them computer proof assistants, but they're not proof assistants. They just make you go 5 times slower. See, so no way will the research community adopt these systems the way we have them right now. No way will the community adopt it. No way are they going to throw away those paper proofs they have. It's hard work learning them, and you go much more slowly than usual. And so that's not the point of these systems right now. Okay, we need other ideas. When I view these systems in the future as being like, I view them as they're going to be help to mathematicians, but they're not going to replace mathematicians, and they're certainly not going to replace our kind of bad but mostly okay literature. So where do these computer proof systems fit into the future of mathematics? That's the last thing I'm going to talk about. So the first very natural suggestion is some digitized databases. Right now, there's plenty of digitized databases for mathematics. We have digitized tables of real numbers. If you do an integral and you do the integral to 40 decimal places, and you're looking at that integral thinking, what is this? Is this actually, you know, is it e over pi? Maybe it's e times pi squared or something. You know, e times pi squared times the square root of 2. You've worked it out to 40 decimal places. You can look it up in a table of real numbers. Right? It's actually, you know, these things exist. You say, oh, I computed this integral to 10,000 decimal places. Here's what I got. And the database might say, oh, yeah, actually, that's pi squared over 4. You see, so, you know, these databases are important. There's databases of integer sequences, right? But also there's databases of all sorts of other things, right? There's databases of music. We digitize music. We turned music from an analog thing to a digital thing. And then suddenly we had the CD. And now, you know, and then suddenly we had, you know, live streaming music websites, and we have Spotify. We turned text from etchings on a page. We've turned that to, you know, characters, and then to, you know, and then to digitized characters, computer text files. And now we have PDFs, right? Digitizing things makes them more flexible. You turn things from an analog state into a digitized state, and they become more flexible. So maybe we should start digitizing mathematical proofs, right? What mathematics should be digitized? Sure, yeah, sure, we should digitize, you know, we should make tables of elliptic curves, we should make tables of modular forms, we should make tables of real numbers. We should make tables of sequences of integers, but maybe we should digitize mathematical proofs, right? Which proofs should we digitize? We can't digitize all of them because there's just too much, but we can start to digitize some of it, right? So maybe we should digitize undergraduate mathematics, all of undergraduate mathematics, because do you know what? Nobody got round to doing it yet. Digitizing all of undergraduate and MSc level mathematics in one system. And we haven't finished. This is what's so ridiculous. So let me show you some of these links. Let's go to the first link here. What's this? Here it is. Here is Lean's maths library, right? And you can see there's a bunch of stuff here. Let me make the font bigger. There you go. We have a folder for algebra, a folder for algebraic geometry, folder for algebraic topology. You know, there's some folder of stuff we don't need. There's field theory, group theory, measure theory. We're slowly beginning to, you know, let's have a look at it. There's algebra. What have we got in algebra? Again, we've got a huge amount of stuff. We have groups, rings, fields, ordered monoids, you know, just goofy stuff that you don't even know you need. You know, quadratic discriminant. We have things like quadratic reciprocity. You know, can we make sense of some of these files? You know, I don't know. Have we got yeah, I don't know. Can we make sense of rings? Like we could look at ring quat. What's going on here? And now you see, now we're beginning to start trying to work out what's in this library, and it's kind of, it's all of a sudden it's incomprehensible computer code. So somehow we've gone too far. We were looking around, we were seeing some sort of overview of what was going on. But when you click too far, you go too far. And that may be for someone that's just beginning to try and figure out what's there. That's not the place to look. Here's the place to look. See, we have documentation all online. This is the Lean Prover community website. We have documentation. Let me stick that in the chat as well. And if you want to look through the documentation, this is a great place to start. You see, it carefully explains, this file we're looking at here, basic properties, the definition of a ring, the definition of a semi-ring, that's a ring without minors, and homomorphisms of rings. And you can read what people have written. This is a much easier thing to understand. So we're building undergraduate mathematics, and we even have a website. If I go to the community websites, if I go to this website here, we have a community website, and here we have explanations. So this is the thing I should post in the chat. This is the place to dive in. Lean community website. This answers the question: what mathematics has been done in Lean so far? And somewhere we have a list of undergraduates. Where's our undergraduate mathematics? Here we are, undergraduate maths. Here's all the undergraduate maths that we've done, right? And there's still a list. Here's some undergraduate mathematics that we haven't done yet, right? It's still being built, but we need to get all of it in one curriculum, in one system. That's where we're going. So there you go. So let's get back to the talk. So there's a reasonable question: why are we digitizing undergraduate mathematics? What is the point of teaching it to a computer? And I think that there's going to be lots of applications. Firstly, we can gamify it, right? Once you've digitized it, you can gamify it. One of the things I do in my introductory course, I teach the Introduction to Proof course at my university, and I teach people about how to define the natural numbers using Peano's axioms. And once you have the definition from Peano's axiom, 0 is a number, the successor of a number is a number, and that's it, right? That's all you can do. 0 is a number, and given a number, you can take its successor, the number after that number. You see, when you're teaching children mathematics, the first thing you do is you teach them to count. 0, 1, 2, well, maybe you start at 1, 1, 2, 3, 4, 5, 6. That's the first thing you teach children. You're teaching them about the successor function. And then once you've taught them about the successor function, you can begin to start teaching them addition. So here's this natural number game. This is a game I wrote, right? This is a fun little game, but I specifically wrote it to teach my undergraduates how to do proofs. How to do proofs in the basic theory of Peano arithmetic. You see, so where's this first? There we go. You see, this is turning Peano arithmetic into a puzzle game, right? Here's the puzzle. For all natural numbers n, we have 0 plus n equals n. So how are you going to prove that 0 plus n equals n? Well, you're going to have to figure out what the definition of addition is. You're going to have to figure out exactly what is known about addition. So it turns out that n plus 0 equals n, that's one of the axioms for addition. But 0 plus n equals n, that's not one of the axioms, so you have to prove it. So you have to prove this thing by induction, right? Induction n with DHD, there. You start off with induction, and now we've got two goals, right? We've got the base case. We have to prove that 0 plus 0 is 0. And then the inductive step, if we know that 0 plus d is d, how do we prove that 0 add the number after d is the number after d? So this is one of the early levels in my game. And if you want to go, if you want to start at the tutorial world of this game I wrote, me and Mohammed, this guy Mohammed Padrampa, he did all the web coding, and I wrote all the lean code. And so this is kind of a fun game to play. This is a really good introduction to lean. Introduction to lean. Lean by the natural numbers. So this is another way that undergraduates can begin to start learning about how this stuff works. So we can gamify undergraduate mathematics. We can write more games. So I just wrote this game. It didn't take very long. We should write more games, I think. Why not? Learning mathematics by playing puzzle games is a really great idea, I think. What's next? Of course, if students have actually learned enough that they can start doing their homework in these systems, once they get better, we can, students can learn that. Already, I have students that can do this already, right? Students that have become experts in Lean. I set my homework in Lean, and students can answer the questions in Lean. And they don't, sometimes it's like, well, I have a proof, but I don't know if it's right. You don't have that anymore. If it compiles, then it's right. So computers can mark homework, right? We can make really interesting tools. We can make interactive, error-free, web-based undergraduate texts where you read the words. If you're not sure on something, you can click on it, you can zoom in, right? And at the end of the day, you can find the formal, careful statements that are being used, a complete list of everything that's actually going into these proofs. If you don't understand something in the book, you can dig in and see more details, because that at the very end of it, we have all the details right down to the axioms. What else, right? Formalize, past. That should say past. P-A-S-T. That's a misprint. Let me see if I can. Can I do? If I change it in the source file to this, I'm using something called Reveal MD. There we go. I'm using it for the first time. This is why we had dots where there weren't supposed to be dots. I'm just getting the hang of it. I think it's really. I used to use Beamer. I'm using this. I think it's really nice. Formalize past exam questions and solutions. Why not? That would be interesting. An interesting place for revision. And all of this we could start doing right now. These are projects that one can work on right now. Make some new games in Lean. That would be really good fun. If you're a university lecturer, start giving out your homework in Lean for those that are interested. They don't have to do it in Lean, but if you want, why not? So that's maybe where undergraduates could find it handy. What about PhD students? Well, do you know what? One of the big problems you have as a PhD student is you have to, you're suddenly you graduate, you get a PhD place, suddenly you're a PhD student in algebraic geometry. Algebraic geometry is a gigantic area. How are you going to learn it? Right? You try to work out what's going on. You have a basic question about algebraic geometry, and what are you going to do? You could ask your advisor. What if your advisor isn't around? What if it's 3 o'clock in the morning? If you want to know whether some theorem in algebraic geometry is true, you can Google for it, right? But it doesn't work very well. If somebody asked that question on Math Overflow, then it will work quite well. But if your question hasn't been asked, maybe it's too easy, right? Or maybe it's just a standard consequence of 2 or 3 known theorems. How are you going to find it, right? Search is a problem. But the Stacks project, it turns out, this is a big undergraduate database of theorems in algebraic geometry. And the Stacks project, if you digitize the statements of that would be much easier than digitizing the book. You just saw, it was easy. I wrote down the statement, there were infinitely many primes, and you could read it. It just said, for all n, there exists a p, such that n is at least p and p is prime, right? Digitizing the statement was easy. Digitizing the proof, you could see from first principles, it takes some work. But if you could just start digitizing the statements, many, many statements in algebraic geometry, why not? We've got the tools to do it. Then you've got a gigantic digitized database, and then you can start asking computer, you can start asking AI, or you could start asking, tools to say, is this theorem in your database? Or is this theorem a consequence of 2 theorems in your database? You see, all of a sudden you've got, you've squared the number of theorems you have access to. Or is this theorem something you can build easily from a much more general theorem? And all of a sudden, PhD students can start typing in there. If you can type in the statement of the theorem in Lean, you can then say, can you make a proof of this statement using the facts in the database? So that should be possible as far as I can see, right? I don't see any reason why that shouldn't be possible, right? So we can make technical search better. Oops. What just happened? We can make technical search better, I think, and so do lots of computer scientists. All we need is people to start slowly digitizing the Stacks project, and then we will have an amazing tool which will make learning algebraic geometry easier. So it might be possible to turn this stuff into things which are useful for PhD students. So finally, what about researchers? People like me, fancy people doing the Langland's philosophy and interested in proving great theorems, right? How are we going to use these primitive tools? They're only primitive because we're not using them, right? I specifically showed you a proof that was kind of taking me a long time. and try to give you the impression that actually these things are quite slow. But do you know what? There's been some recent news, right? So last December, Peter Scholze, the fields medalist, he challenged the computer proof community, right? He asked if computer proof checkers could actually check a theorem that he'd recently proved with Dustin Clausen. So I asked him to write a blog post on my blog. So here's the blog. He wrote this blog post. This is my blog, and Scholze wrote a blog post challenging the formal proof verification community to prove some technical theorem that he just proved the year before. And some people, some expert mathematicians thought, we're going to have a go at this. And initially, everyone was like, well, it's going to take years. But we worked and we worked, and 6 months later, we had something. We didn't have a proof of the thing he wanted us to prove, but we had a proof of a key technical statement, which was like halfway there, if you like. And this was the key technical statement, which Scholze was worried about it. He asked us if we could prove it because he said he's read the proof. In fact, let me tell you the story. What happened was Scholze said to me, did you have a study group on my paper with Clausen? And I said, yeah, we studied it at Imperial. You know, a group of people met for a couple of hours a week, and we read through your proofs. And he said, did you check the technical details of the proof of theorem 9.4? Did you go through all the technical details? And I said, no. You know, it looked plausible. We just assumed it and went on from there because we only had 2 hours. You know, this is the kind of thing that would take weeks. And he said, everyone I ask says this, right? Nobody is checking the proof nobody is checking the proofs of these technical arguments. And this is completely a new kind of mathematics. Someone needs to check the proofs. Can a computer check the proof of this technical lemma? So we've checked the proof of this key technical statement. And Peter was really excited, right? This is what he said. I'm excited to announce that the experiment has verified the entire part of the argument that I was unsure about. So he was a researcher. He wanted some other people to check through his proof. Humans weren't doing it. We got a computer to do it. He says he found it insane that interactive proof systems are now at that level, you see. So they're much better than what I was showing you. I was trying to kind of make out that they're kind of primitive, but actually, once you become an expert user, you can start doing stuff fast with them. Within a reasonable time span, they can formally verify difficult original research. So let me oops, that wasn't clever. I'll post some links at the end. So you can read more about what Scholze said in the links in the chat. I'm about to post some things. So the final part of the story is AI, right? What about AI? You know, can we get computers, can we get AIs to be better theorem provers than mathematicians, right? Humans taught computers to play chess in the 1970s, okay? And I played a computer at chess in the late 1970s, and it was terrible. It would spend a very long time thinking about its moves, and then it would make a terrible move. You know, it wouldn't throw away material, and believe you me, if you left it so it could fork your king and rook, it would fork it instantly. But computer chess programs in the 70s were terrible. In the 80s, they became better. You know, then they became kind of club standard. And in the 90s, they became better than the world chess champion, right? That was the progress. But one of the key components was a huge database of expert games, right? And that's what we're missing with Lean, right? Will computers one day start to beat humans at proving theorems? This is this is an analogy, right? But there's a key difference here, right? There's a bunch of optimistic AI people, but the thing is, there's a big difference between mathematics and chess, and that chess is played on a finite board, whereas mathematics is infinite, which to me, that seems like a big difference. But is it going to be possible? Well, do you know what? Maybe. But the thing is, it would be one thing that might help would be a big database of mathematical theorems. And that's what I want to, I may be concentrating more on things like algebraic number theory and algebraic geometry, because I would like computers to start proving theorems in algebraic geometry, right? But who knows? If you want to see computers proving theorems in combinatorics, then come along and start formalizing theorems in combinatorics. We have some, we have basic theorems about graphs. We have Hall's marriage theorem and things like this. But it's people like you that are growing the data. I should say this: Lean's maths library is great. It's being written, at least in part, by undergraduates, right? I keep talking about experts in the system, but some of these experts are undergraduates and MSc students who have just been working with me, and I've trained them how to use the system, and they're becoming experts. So, okay, that's pretty much all I want to say. Here's an advertisement. I have an Indian PhD student, Ashwini, and she has been using Lean for 2 years now. She's an expert in Lean, and she knows this guy Cody. He's a student of Jeremy Avigad at the University of Pittsburgh. And we were just doing something called Monsoon Math, which is working with a bunch of kind of like, Math Olympiad-like kids who are still at school. And Ashley and Cody wrote some kind of Lean material that they hope will be useful for these very smart high school kids. And there was a lot of enthusiasm. And so they said, okay, well, maybe we can start meeting weekly and start beginning to teach young Indian kids how to do mathematics in Lean. And so they're going to run things on they're going to run things at sometime in the evening, Indian time. But this is already a bunch of smart high school kids. And if any of you IASC people want to get involved, here's Ashwini and Cody's email addresses. They said you should just email them. So they're running a Lean course for intro mathematicians, and the idea is teach you how to contribute to Mathly. So that's what they're doing, and it's probably going to be Saturday evening. So if you're interested and if you're free, then do feel free to come along. That's it. Thank you very much for listening. Thank you very much for coming. And I'm now going to look through the chat. So maybe I'll pause because perhaps the organisers have got something to say. I'll pause now, but then the questions that have appeared in the chat, I'll try and deal with them now.
I think you can first go through the questions which they have, and then perhaps we can.
Okay, that's great. So, human computers. Yes, I'm well aware that there have been some spectacular human computers. Indeed, there have been some spectacular Indian human computers. The question is, calculators are very small because they've typically only got a 10-digit display, but just use a computer algebra package. Look, here we go. Here's my computer algebra package. Let's go back to this. Look, here's an extremely large number, and we can multiply it by another extremely large number. So this is far bigger than your computer can handle, but look at this, it's just done it instantly. So you see things, and you want to extract a 20, let's take the 21st root of that to the power 1/21. Let's try this. You see, we can there it is to like 30 decimal places. So if you want to do computations, then you need to choose the right tool for the job. If you want to prove theorems, then it's a computer proof system. But if you want to do computations, then there's many computer algebra systems. I joined late. Which software was using to prove? I was using Lean. Oh yeah, that's been answered already. Thank you very much, chat people. Lean community website. Thank you. Industrial. Anish Hevar. Can computers help in the development of complex mathematics involved at the very fundamental scale of our universe? Well. The moment you start talking about the universe, then you're talking about physics, right? So there's the kind of mathematics I've been focusing on right now have been stuff that's been going on, in the mathematical universe, the Platonic universe, if you like, or the formalist universe. I don't want to talk about physics, but the thing is, string theory is a mathematical foundation for physics. So string theory, you can absolutely begin to formalize how that works. You can add axioms if you want axioms. You can prove theorems. And also you can start, if you start making doc strings, then you can start using programs that will generate web pages, which will present Lean code in a very beautiful way. We're currently working on making this even better, by the way. Right now, if you saw, I guess I showed something about is it still there? This sort of stuff here. I showed something about the API documentation here. Like if we want to learn something about primes, whatever prime numbers. We can search for prime numbers, and then we'll see, we'll maybe find something. There you go. So what's the definition of a prime? There. So here's some stuff. You see, this is maybe the wrong kind of prime. This is a prime element of a commutative monoid with zero. So this is a very algebra definition of prime. And you can learn about these things here. But you see, there's no pictures. So we're currently working on a system where there'll be some pictures as well. So we should be able to make some interactive document where we have the mathematics explained in a human way, and then mathematical equations which you can click on, but also diagrams as well which you can click on. And it's just been going through the natural number game in the examples. When will I be able to write my own tactics? If you go to the Lean Prover community website, there's a short series of 6 videos, 6 short videos which explain the beginning of tactic writing. That's the answer to that question. So the Lean Prover community has its own YouTube channel. That's where you should be going for that sort of thing. The community YouTube channel. Automated theorem proving. That's not something I know so much about, although I appear to be organising a conference in it very soon. What about automated theorem proving in computer? This is sufficiently far from my area of expertise. I mean, I know people that work in it, but to give an example of the kind of things these people can do, you can have a gigantic Sudoku problem, or a gigantic puzzle game of that form. And these automated theorem provers can try and solve these things very quickly. But the thing is, I personally am interested in research mathematics. And a lot of research mathematics, it seems to me that interactive theorem provers might be more helpful than automated. I mean, Lean aims at, what the goal is with Lean, of course, is to get one system which has both of these things in. An interactive theorem prover and an automated theorem prover all in one system. Leo Demara, the guy that wrote Lean, he also wrote Z3, which is an ATP. Is there anything else? This might seem overly optimistic, but do you think ITP could prove the... You see, this is what I think it will take a while before we see this, right? This is somehow the problem. But we just don't know until we try, right? This is the question. Will a computer come up with a proof of the Riemann hypothesis? This is a great question, right? And some humans are incredibly skeptical, and some AI people are incredibly optimistic. And I sit somewhere in the middle. Right now, I would like to see a computer come up with a proof of something, right? I would like to see computers begin to show some kind of indication that they can think independently. Come up with a proof of something where they haven't been told a map to the proof. Right? I'm on an IMO committee. We're trying to get Lean to solve IMO problems. And right now, the main goal of this committee is to write a tactic which will get a gold medal in the IMO. If you formalize the questions, Lean will come up with the answers. But right now, I think here's a much more reasonable goal. Can we come up with a tactic that can get 1 point in an IMO? I think this is a not unreasonable question. Can we integrate? Yeah, we can do differentiation and integration, sure. You just have to import the right libraries. We proved, but not numerical, right? You can't do numerical ones. I can't evaluate the integral of sine x from 0 to pi as a real number to 100 decimal places. But what I can do is I can prove that the integral of sine x from 0 to pi is whatever it is pi. That's the kind of thing we can do. And I can prove that the integral of sine x from 0 to 2 pi is 0. That's the kind of thing that can happen. So those are chat questions. My time is over. I've had my hour, but I'm more than happy to stay around for a while if anyone wants to ask. Yeah,
you mentioned that proving, I think, technical some lemma 9.4 or something was the technical step, right? How long was this in terms of actual computer code? Yeah.
I can post you a link to it. Let me try and find the link. Lean tense. So Lean liquid. So right now, here is the. I write in the chat and it doesn't go to everyone. I can only post direct messages to Pravega. Sorry, I've just understood this. I'm posting these messages to somebody, and this poor person has to then forward them to everybody. Let me just find this here. Let me just post it here. Right, let's go here. So here is the repo that proves this thing. And right now it just looks like the Mathlib repo, but now you see you have kind of complicated things. You have like Breen to Lean and Prop 8.19 and Prop 9.2. And here we're developing theory of pseudo-normed groups and systems of complexes in an abelian category. So that's what it looks like. And then, but yeah, how big are these files? Here's a random file, the normed snake lemma. How big is this? This is 126 lines long. Let me just type. Yeah, my guess is that right now we have about 5,000 lines of code. But also, remember, we have 5,000 lines of code for this proof of this theorem of Schulze, but also we're using the maths library, right? This is not part of the maths library. This is a separate project. So 5,000 lines of code to prove this theorem of Schulze, but using Lean's maths library, and Lean's maths library is currently 600,000 lines of code. 600,000. That's how much it's grown in the last few years. It's been absolutely incredible. When I started, it was tiny. The statistics here, look. So you know, this is what we're using. We have 58,000 theorems in the maths library. It's just kind of shooting up and up and up. Here was lockdown. You can see it was going at a certain rate, and then we had, you know, then COVID appeared, and then you see the derivative went up because when people were locked down, they had more. They were kind of stuck in their rooms, so they did more coding. And now you see the places slowly opening up, and now you see it sort of going down again. I thought this was a very interesting COVID effect. And there you can see the commits as well. So you know, a small number of lines of code, but we're using a gigantic mathematics library that has all the theory of groups and rings and fields and vector spaces and topological fields and topological rings and all the stuff that's needed. So it's difficult to say, you know, how long the proof is in total. Since Lean has the biggest library of digitized maths, what is the project of ATP and Lean as a tactic? Well, that's going to happen, right? Because all we need to do is someone needs to ask Leo to integrate Z3. It's absolutely going to happen. I mentioned proofs, errors in proofs written by humans. What about errors in computer code that bleed into proofs? Yeah, okay. So there's several things, right? Firstly, do you believe the human when they write down the proof, or do you believe the computer when it writes down a proof? I would say the computer is an order of magnitude more likely to be correct, right? Humans make mistakes. I have been lecturing a certain course for many years. I was lecturing graduates commutative algebra, and I was proving something called the Hilbert basis theorem. And I gave the same proof year after year to smart MSc students at my university. You know, Imperial is a bit like, you know, the IASC. It specializes in the sciences. And you know, and it's a decent place. And I was giving this proof to several people, you know, to many people over a period of years. When I started proving it to Lee, Lee got really obnoxious about something. Lee was like, "Why, you know, you say this polynomial x has got degree 1, the polynomial x, right? F of x equals x. You say this polynomial has degree 1, but how do you prove it?" And I was just like, it's obvious, library search, it's obvious. And library search doesn't find it. And it's just like, what, the degree of x is 1, right? And then I started digging around, and it turned out that if the base ring is a 0 ring, if we're not working over the reals or the complexes, but if we're working over the 0 ring, then x is not, the degree of x isn't 1, because x is the 0 polynomial. So the degree is negative infinity. So there was this dumb mistake in my proof. My proof didn't work for the 0 ring. And I'd never noticed, and all the people I'd shown it to never noticed. You know, you get some clever clogs in the audience who's like, ha, 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 this proof doesn't work for the 0 ring. It's like, okay, you know, touche, you beat me. Lean is like that. Lean spots these problems. So Lean is much better than humans. Much better than humans. But is it perfect? Well, let me just tell you this. If we get Lean to make a proof, Lean does a whole lot of work making the proof from what the humans type. The humans type high-level things. Lean does a lot of work to make the proof. But that proof is just a big, gigantic tree, right? It's a gigantic structure which is unreadable to a human, but which is understandable by a computer. And you can take that structure and you can give it to a type checker. and say to the type checker, is this a proof of this theorem? And the type checkers, there's 3 or 4 type checkers for lean, and they're all written in different languages, and they're all very, very small. And you give it this graph, and you say, is this a proof of this theorem? And the type checkers check it instantly and say yes. So that's the, if there's an error in the lean kernel, but it still produces a correct proof, then the type checker can verify that this is a correct proof. And you can, and if you're worried about the chipset, what lean was written in C++, maybe there's a serious bug in C++, but the type checkers are all written in other languages. They're written in Scala and in Rust. So you get more and more, this is what you do, right? If you really want to be 100% sure, you take your theorem, you prove it in lean, you take the graph, and you verify it in 3 different type checkers running on 3 different operating systems, written in 3 different programming languages. And by that point, it's getting to the point where you can kind of say, we are as sure as humanity could ever be sure of a statement. That's what I think. Besides syntactic differences, what differentiates lean from the other programming languages you mentioned? One, to be honest, the main difference as far as I'm concerned is that there are far more mathematicians using lean, and there is far more mathematics being done in lean than in the other theorem provers. And now we have to stop and say, is that a good thing or a bad thing? Right? Because these other theorem provers have been around for a very long time, but they're being used by computer scientists. They're mostly being used to verify things that, like code has no bugs, or to do foundational research into type theory. And the big question is, that's okay, foundational research in type theory is important, but how about we do hard mathematics? How about we do Schulze mathematics in lean? And I talk to people in the other systems, and they're not really interested. Most of them they're just doing other things. The focus of the community is on other things. And one of the main focuses of the lean community is on doing research level mathematics. Building up our system until we can start proving more theorems of Schulze and more theorems in algebraic geometry. And to do that, we're having to make this library from scratch. And we're making undergraduate mathematics. We're still not done. We're making MSc mathematics. We're making modular forms. We still don't have modular forms. We're slowly doing it. But the other systems, they don't have modular forms, and there's nobody working on them. That's the difference. So if you want to do modular forms in the computer proof checker, try any system, because we haven't got them yet. But if you try the other systems, you'll find it hard to find people that will help you. Whereas with lean, there will be people falling over to help you. There's already several people just working on modular forms. We're slowly building the thing. So that the community is the difference, right? The lean Zulip chat, that's a place. The lean Zulip chat is not a chat room. It's a really it's a focused, highly serious, research environment. And there's people talking all the time about lean. It's very focused and on topic. So the community is the main difference. Theorem proving strategies, I don't know. I've never used the other systems. I'm really not, I'm reluctant to comment. They do things in a slightly different way. It's probably different. I don't know if it's easier or harder to do Schulze's work in one of the other systems, because nobody's done it yet. And it seems to me that nobody will do it. Why don't you go ahead and do it? We'll find out. Maybe the other systems are better. This is an interesting open problem. The other thing is that lean has got the backing of a multi-billion-dollar corporation behind it, whereas these other systems are just run by small research groups. So, I'm over 50 years old. I'm going to choose lean because it's the quickest path to happiness. That's the answer to that. Any more for any more?
There don't seem to be no chat questions. Sanjeev, did you have anything to say?
No, nothing much.
Fine then. We can conclude the talk then, I guess.
Well, thank you very much for having me. And if you're interested in learning some lean, then get in touch with Ashwini. She's a smart girl. She's formalizing Iwasawa theory in lean. She's formalizing right now she's doing the p-adic zeta function. And but she's going to be a great teacher, I hope. I really think she will be.
All right then. Yeah. Thank you, Professor, for this wonderful talk on theorem provers and how they can be useful in future work in mathematics. I hope the audience enjoyed the talk, and maybe in the future a few students could contribute to this project of yours. So yeah, we hope that the audience enjoyed the Enumeration talks, and maybe they'll work in the future if they're interested in such things. You're improving, yeah. I don't know if you know about this, but there's someone in IIC called I think Siddharth Gadgil, who actually was an automated theorem proving.
Yeah. I know his name, but it's not. I just know much less about it. I've only been working in this area for a few years myself. I need to bone up on these things. I'm organising a big conference with about ATPs, with Terry Tao and Tim Gowers and Marijn Hoyler and Jeremy Abigad. We've just begun. We're going to start throwing in proposals. So give me a year or two, and then I'll be able to say something more useful. Yeah. Come to the conference. Okay.
Yeah, that was it then. Yeah.
Thank you. Bye-bye.
Bye. Right.